Now, let's follow PowerPoint slides here. So first, pitch mechanism. First of all, why do we think about the mechanisms of pitch? We just have had demo of how we perceive pitch out of complex tone. The question is, why do we really care about this? The answer is we'd like to understand our ability to discriminate pitch of tones with similar frequency, and then we need to come up with explanation or model of how we do that. This way we have a good idea of how and why people with sensory neural hearing loss have trouble with discrimination of pitches. So in this slide, first, pitch mechanisms. So when do we listen to a pure tone such as 500 hertz tone, how do we perceive its pitch? There are two theories, two mechanisms that we understand pitch. One is temporal based, another one is place based. So the temporal based means that from the waveform, from the periodicity of the waveform or the peaks of the waveform, we follow the pitch. So that's the theory. The second mechanism, place pitch, is based on the excitation on the basilar membrane, which is basically the spectrum representation of the spectrum of the signal. So the excitation of the basilar membrane. So next slide, temporal versus place theory. So the temporal is based on the waveform, or when the sound wave comes into the ear, and the signal is received by auditory nerve fibers. Auditory nerve fibers are following the temporal waveform, up down waveform, and then when nerve fibers show these patterns, they show the very well organized patterns in time according to the wave. So that's what we call phase locking. So the idea here is that the brain somehow looks at this pattern of phase locking and decode or perceive what the pitch of this sound is, what this tone is. So it is really periodicity based, and we don't know exactly how it is done, but this is done by the brain or the central auditory mechanism. See, here's a caveat. The phase locking, as we know from physiological studies, phase locking weakens as we look at frequency with high frequency tones. So phase locking weakens and about 3,000 hertz tone or so, and then above that it really disappears, which means that auditory nerve fibers are not capable of following the temporal periodicity of the waveform, which means that temporal based or periodicity based pitch mechanism will not work in high frequency, such as 3,000 and above, 3,000 hertz and above. Second, place mechanism. Place mechanism is basically it explains that we perceive and discriminate pitches based on the spectrum of the sound or the excitation, the peak location of the excitation pattern on the basilar membrane, which is which is fairly good. And we have this picture here. So we have one peak and another peak, and we see this very small delta F. And here's the thing. Place-based pitch mechanism works pretty well for high-frequency sound, which is actually natural because for high-frequency sounds, such as over 3,000, we just said that temporal mechanism will not work, so there should be something that works, so which is a place mechanism. That's great. On the other hand, if we try to explain our pitch ability, our pitch judgment or pitch discrimination ability of low-frequency tones, such as 500 hertz or below, the place mechanism does not really work. Here's the reason. We have this picture. We have this excitation patterns, two patterns that are quite overlapping really closely. The thing is, explanation or model based on the place or these excitation patterns do not really explain how we really our ability to discriminate 500 hertz tone or below, because they are so close, they are so overlapping as we look at frequency as we look at excitation patterns of the lower frequency tones. So place mechanism is not going to really work well for low frequency. So here's the summary again. Here's the summary. For high frequency, temporal pitch will not work, and place pitch is dominant. And for low frequency, place mechanism is not going to really reliable. Instead, temporal periodicity is going to be more reliable. Then in the middle, like between 500 and maybe 2000 hertz or so, between that area, that frequency region, both mechanisms work together. So now, next topic is J&D, or just noticeable difference in frequency or pitch discrimination. The question is, what is the J&D? So what is the smallest difference in frequency that we can tell the difference, we can discriminate? So if someone asks you how sensitive are we to the pitch change of sound, how would you answer? Will you just say, if someone asks you to give them a ballpark answer, such as 1 hertz, 2 hertz, 5 hertz, or 10 hertz, then how would you answer? Even if you don't know what to answer, you should still know how to answer. Okay. So just don't answer like, maybe it's 1 hertz or 5 hertz or 10 hertz. Just don't answer that, because always remember Weber's law. Weber's law is something to remember, something to begin with. So in theory, the smallest difference in frequency or J&D we can discriminate is proportional to the frequency of interest. That is just paraphrase of Weber's law. So we can actually phrase Weber's law in so many different ways. One way is like delta F, in this case frequency, so it's F, delta F over delta F for J&D, so the smallest delta F. Okay, delta F over F is constant. So that's one way to answer. Then one way to describe, one way to phrase Weber's law. Another way to phrase Weber's law is because delta F over F is constant. In low frequency, J&D itself is small, and for high frequency, J&D increases accordingly. So that's another way to phrase Weber's law. So if the J&D was 2 hertz with a 400 hertz tone, just for example, okay. So in this case, that means that we are able to tell the difference between 400 and 402 hertz. So we can discriminate these two tones. So in this case, J&D was 2 hertz, okay? But then J&D would be 4 hertz if we considered 800 hertz. So you just cannot just say J&D is how many hertz. You just cannot say that, because it always depends on the frequency of interest, the frequency that you are looking at. So in this very example, what is the Weber's law? Okay, so that's something to think about. It's fairly simple. I'll just move on. So the problem here in the Weber's law is in reality does not hold true. Again, it is a really theoretical guideline that we base our observation on, but it is not really working really all the time. Practical issues are, for example, it depends on our ability to tell the frequency difference, small frequency difference, really depends on how we measure. Okay, so how we measure. So there are two ways to measure our ability to discriminate frequencies of tones with similar frequency. One is direct measurement of J and D by playing two tones back to back. Another way to measure is using FM tone or frequency modulated tone. So here in the slide I said two ways to measure and DLF or FMDL. Here DL is just another term for J and D. Again, J and D stands for just noticeable difference, and DL stands for difference Lyman. Those two are just synonymically used. So first, direct measurement of J and D, we just call DLF. We play two tones that are close in frequency back to back and ask the listener which one is higher in pitch, and to see if they can tell the difference in pitch. So for example, if I want to measure J and D at or around the frequency of 500 hertz, then I would play 500 hertz tone and 500 plus some difference we call delta F, so such as 510 and back to back. So here's an example: 500, 510. If you listen to these two tones back to back, can you tell the difference? And do you know which one is higher in pitch? 510 and 500, they are fairly easy for us to detect the difference. So usually normal hearing listeners have no problem discriminating the two tones. So that's easy. Then we make the difference smaller. So for example, 500 and 505. So here's an example. So if that's still easy, then you go down further, like 500 and 503, for example. Okay, so you just change the difference between the two tones systematically, smaller and smaller, till the listener cannot tell the difference. Okay, so that's how we measure DL or J and D in frequency directly. Okay, so that's one way. Another way to measure J and D is using frequency modulated tone. Okay, then for this one, we first need to know what frequency modulation is. So a couple of weeks ago, we talked about amplitude modulation, right? So we know what amplitude modulated tone means. Basically, a tone as opposed to having constant amplitude like this, we can actually modulate the amplitude. Wow, 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 wow. Okay, so that was amplitude modulation. This one, amplitude is constant, okay, that is kept constant, but the frequency of the tone is changing. So for example, the same purpose, we want to find out our sensitivity to change in pitch. So if you want to measure that around 500 hertz, here's how you can make FM tone. We can create an FM tone the frequency is modulating between 500 and 500 and something. For example, we can make 500 and 550. Okay, just make it easy. So here's one example of FM tone between frequency modulating between 500 and 550. Okay, that's what FM sounds like. So FM is like a siren. In this very example, the swing of modulation is only 50 hertz, so it's not really big. But like the siren sound we hear, usually really long, big swing, like 500 and 1,000, for example. Okay, just for reference, this is what siren sounds like. So FM with a big swing. Okay, so that's really what FM is like. But for this for this very particular testing, to measure JND or frequency, JND or difference alignment, we are actually using very, very small swing. So the modulation may not be so obvious, but we are still trying to tell whether that is this tone is modulated, frequency modulated or not. So again, here's a 500 and 550. And so that because this is obvious, it's relatively easy to tell that there is modulation, there is a frequency swing. We can make the swing smaller and smaller. So here's another FM tone between 500 and 510, okay? Can you tell that there is modulation, there is swing? You should be able to do that. It's fairly, as long as the volume is good enough, then you should be able to tell that there is a swing. If we go further down, like 500 and 505, here's what it's like. Okay, it's getting a little harder. But anyway, so just systematically make the swing of modulation smaller and smaller until we cannot tell the difference, until we cannot tell that there is a frequency swing. So that's how we measure frequency, JND frequency or difference alignment. So these two methods we just covered. The first one is direct measurement of JND or DLF. The second method is called JND measured with frequency modulation. So we just call it simply FMDL. By the way, which one of these methods is really better? It's right way to do. There's really no way to tell which one is better, which one is better than the other. Each one has their own meaning. Sometimes we need to be able to tell whether two tones that are played in sequence are different in frequency, or sometimes we need to tell whether the tone we hear is modulated, frequency modulated or not. Frequency modulation, you may not be familiar with the terminology, but that is actually, in nature, it occurs a lot. Siren was one example, but there is more extreme example. Another example of frequency modulation is like the bird chirping sound of birds. Also, even our speech, when we make our voice, when we speak, we actually swing. We may actually make modulation of fundamental frequency of our pitch up and down to carry meaning, emotion or other linguistic meaning. You like ham, or you like ham. So in this very example, I just modulated the pitch differently between two sentences to have different meanings. Okay. So this frequency modulation is actually it's going on a lot in daily life. We just don't realize it. So there are two ways to do this. So so this is it. So look at this slide. This picture is from textbook. So this is the result of frequency discrimination in two different methods. So one is DLF here, the other one is FMDLs here. Look at the y-axis here, okay? So y-axis, what is it? It says frequency DL as proportion of center frequency, which is basically what? Basically delta F over F, which is the Weber fraction, okay? So Weber fraction was what? According to Weber's law, it was supposed to be constant, right? So now look at the result here. There are two ways. So first of all, this dotted line here is the result with FMDL. So if you look at this, y-axis is supposed to be constant across all the frequencies. It should be like this, right? So if you compare these two methods, the second method, FMDL, actually shows you sort of better answer, or answer that is close to what you would have expected from Weber's law, meaning that it's constant. So if you follow some of these values, it's sort of like this. So somewhere like, what is the value here? It is 0.005. 0.005 means that it is about what? About 0.5%. So approximately speaking, so what is it? What is 1% of 500? 1% of 500 is 5 hertz, right? 5, right? So now it is 0.5%, so half of 1%. So it is about 2.5 hertz. So according to this, if Weber's law, if Weber fraction was 0.5%, then this tells us that our ability to detect modulation, frequency modulation, is about for 500 hertz is about 2.5 hertz. So actually, if you really follow the read line here, this maybe it should actually correspond to about 3 hertz. So about 503 hertz. So that's what it says. But approximately it's going relatively flat, except that it goes a little bit up high, but still relatively good. But if you compare this to DLF, direct measurement of J and D in frequency, it's way deviating from the flat, the constant line. So in lower frequency, it is really about 500 is really low, about 0.2%, and it increases really substantially, significantly, and then 4,000 and 8,000 is really way up high. So about 1% or 2%. So meaning that if we were to play two tones back to back, then our ability to tell the difference in the frequency is getting worse for higher frequency. But for FMDL, if we were to detect the change in frequency modulation, then we are fairly constantly sensitive across all frequency. So there are two different ways to look at this result. Okay.